Saturn, a celestial masterpiece in the vast expanse of our solar system, stands as a symbol of both cosmic wonder and scientific discovery. Its iconic rings, a feature that has captivated observers for centuries, make it one of the most recognizable planets. Composed of billions of icy particles, some as small as grains of sand and others as large as mountains, these rings shimmer like a delicate halo. Beyond its visual allure, Saturn holds mysteries that continue to challenge our understanding of planetary systems, making it a cornerstone of astronomical exploration. As the sixth planet from the Sun, Saturn lies at an average distance of nearly 1.4 billion kilometers from our home. It takes over 29 Earth years to complete a single orbit around the Sun, granting it the nickname the slow mover in ancient times. Despite its immense size, it is the second largest planet in the solar system. Saturn is also extraordinarily light for its dimensions. Its density is so low that if a vast ocean existed large enough to contain it, Saturn would float. This remarkable property reflects its composition, which is dominated by hydrogen and helium, the same elements that fuel the Sun and formed the primordial universe. The planet's cultural and scientific significance stretches back thousands of years. To the ancients, Saturn was more than a wandering star in the night sky. It was a deity. The Romans associated it with Saturnus, the god of time, wealth, and renewal, often depicted holding a sickle or scythe, symbolizing both the harvest and the relentless passage of time. For the Greeks, it was Kronos, the leader of the Titans and the father of Zeus. These associations underscored Saturn's perceived power and mystique, and its steady movement through the heavens inspired awe and reverence. With the invention of the telescope in the early 17th century, Saturn transformed from a distant point of light into a world of breathtaking complexity. Galileo Galilei was the first to observe the planet in 1610, describing it as having ears in a mass, an early and imperfect view of its rings. Later, Dutch astronomer Cassini-Huygens, using more advanced instruments, identified the rings as separate structures encircling the planet. Saturn quickly became a focal point for scientists, representing both the triumph of human ingenuity and the vast unknowns that still lay ahead. Saturn's rings are not its only claim to fame. The planet is surrounded by a retinue of moons, each with its own story. From Titan, with its dense atmosphere and lakes of liquid methane, to Enceladus, with its icy geysers hinting at a subsurface ocean, Saturn's system offers unparalleled opportunities to study the conditions for life and the processes that shape planetary systems. The interactions between the rings, moons, and the planet itself create a dynamic environment where gravitational forces weave an intricate cosmic ballet. In modern times, Saturn has become a hub for scientific inquiry. Missions like Voyager in the 1980s and Cassini, which orbited Saturn from 2004 to 2017, have revealed the planet's incredible complexity. Cassini, in particular, unveiled details about its atmospheric storms, magnetic field, and the interactions within its moon system. The spacecraft provided a close-up view of the planet's rings, showing them as ever-changing structures sculpted by gravity and time. These findings have reshaped our understanding of not only Saturn, but also the formation and evolution of planetary systems throughout the galaxy. Perhaps most captivating about Saturn is its duality. It is both serene and turbulent, ancient yet vibrant. Its rings, seemingly delicate and static from afar, are in constant motion, composed of countless particles colliding, clumping, and dispersing over time. Beneath its clouds, Saturn is a realm of extremes, with roaring winds, vast storms, and a core heated to tens of thousands of degrees. This balance of beauty and power makes Saturn not just a subject of scientific study, but a reminder of the universe's capacity to surprise and inspire. Saturn's exploration continues to pose profound questions. How did its rings form? And why are they so young compared to the planet itself? Could its moons, like Titan or Enceladus, harbor life in their hidden oceans? What does Saturn's atmosphere reveal about the processes that shaped our solar system? Each discovery about Saturn adds another layer of intrigue, drawing us closer to understanding the mysteries of our celestial neighborhood. In the ever-expanding tapestry of the universe, Saturn is a thread that binds humanity's past, present, and future. It links the mythological imagination of ancient civilizations to the cutting-edge technology of modern science. It reminds us of the interconnectedness of all things, from the tiniest ice particle in its rings to the vast gravitational forces that govern its moons. Above all, Saturn stands as a beacon of wonder, inviting us to look beyond and dream of worlds yet to be explored. Throughout human history, Saturn has held a special place in our cultural imagination, representing mystery, power, and the passage of time. Its slow and deliberate movement across the sky distinguished it from the faster-moving planets closer to the Sun, inspiring early civilizations to associate it with steadiness and longevity. Even today, Saturn continues to bridge the gap between mythology and science, serving as both a symbol of wonder and a focus of rigorous study. In Roman mythology, Saturnus was the god of time, wealth, and agriculture. His sickle or scythe symbolized the harvest, but it also embodied the relentless march of time, cutting through the cycles of life and renewal. The planet's association with the god of time is fitting, given its slow orbit around the Sun, which takes nearly 30 Earth years to complete. For the Greeks, Saturn was Kronos, the leader of the Titans, who ruled during a mythical golden age. These ancient associations with abundance and cycles reflect humanity's enduring fascination with the planet, linking its movement in the heavens to the rhythms of life on Earth. Astronomically, Saturn has played a pivotal role in shaping our understanding of the solar system. Observations of Saturn date back thousands of years, with Babylonian astronomers recording its position as early as the 8th century BCE. Ancient Chinese and Indian astronomers also noted the planet's unique characteristics, weaving it into their astrological systems. However, it wasn't until the invention of the telescope in the 17th century that Saturn's true complexity began to unfold. In 1610, Galileo Galilei turned his primitive telescope towards Saturn and was astonished by what he saw. He described the planet as having ears, or handles, an early and imprecise observation of its rings. Galileo's inability to discern their true nature reflected the limitations of his instruments, but marked the beginning of Saturn's modern scientific exploration. Later, Dutch astronomer Cassini-Huygens, using a more advanced telescope, identified the rings as separate structures encircling the planet. He also discovered Saturn's largest moon, Titan, in 1655, opening the door to studying Saturn's intricate moon system. The study of Saturn accelerated in the centuries that followed, as improved telescopes revealed more details about its rings, atmosphere, and moons. Observations by astronomers like Giovanni Domenico Cassini and William Herschel added to our understanding of its dynamic system. Cassini, for whom NASA's landmarked spacecraft would later be named, identified divisions within the rings and discovered several of Saturn's moons. Herschel, meanwhile, revealed Saturn's faint outer rings, further expanding the known boundaries of its system. Culturally, Saturn's symbolism has evolved alongside our scientific understanding. During the Enlightenment, it became a symbol of human ingenuity and discovery, as astronomers uncovered its secrets and refined models of the cosmos. In literature and art, Saturn often represented the sublime, the awe-inspiring beauty and power of the universe that transcends human understanding. Writers like William Blake and poets of the Romantic era drew on Saturn's imagery to evoke themes of time, mortality, and infinity. In modern times, Saturn has become an icon of exploration and discovery. Space missions like Pioneer 11 and Voyager 1 and 2 in the late 20th century provided humanity's first close-up images of the planet, transforming it from a distant point of light to a dynamic world filled with complexity. The Voyager missions in particular revealed the intricate structure of Saturn's rings and hinted at the diversity of its moon system. These missions were a prelude to the Cassini spacecraft, which orbited Saturn from 2004 to 2017, revolutionizing our understanding of the planet and its system. Scientifically, Saturn has shaped how we think about planetary formation and evolution. Its rings, moons, and atmospheric dynamics provide a natural laboratory for studying the forces that govern our solar system. Observing the interactions between Saturn's gravitational field and its moons has helped scientists refine theories about tidal forces and orbital mechanics. Studying its rings has offered insights into the processes that shape planetary systems, both in our solar system and around distant stars. Saturn's cultural and scientific significance endures because it speaks to both sides of human curiosity, the need to understand and the desire to dream. It embodies the intersection of mythology and astronomy, where ancient stories meet cutting-edge science. Whether inspiring awe through its visual beauty or challenging our understanding with its mysteries, Saturn remains a celestial ambassador, connecting humanity's past with its future among the stars. Saturn occupies a unique position in the solar system, both in its physical location and in its role as a keystone for understanding planetary dynamics. As the sixth planet from the Sun, it lies in the outer regions of our solar system, beyond the asteroid belt and separated from Earth by an average distance of 1.4 billion kilometers. This vast expanse has made it a challenging but rewarding target for exploration, offering a glimpse into the workings of gas giants and the broader universe. Physically, Saturn is a gas giant, part of the Jovian class of planets that includes Jupiter, Uranus, and Neptune. With a diameter of about 1,2,0,5,3,6 kilometers, it is the second largest planet in the solar system, yet its density is so low that it could float in water. This characteristic is a direct result of its composition, primarily hydrogen and helium, elements that dominate the early solar nebula. Saturn's immense size and composition make it an excellent model for studying how planets form and evolve in such conditions. Saturn's position in the solar system is not just a matter of distance, but also of influence. Its gravitational pull affects the orbits of nearby celestial objects, including its moons and the icy bodies in the Kuiper belt. Like Jupiter, Saturn acts as a kind of guardian for the inner solar system, deflecting or capturing comets and asteroids that might otherwise threaten Earth and its neighbors. This gravitational role highlights its importance in maintaining the stability of our planetary neighborhood. Saturn's orbit around the Sun takes approximately 29.5 Earth years to complete. This long orbital period results in slow seasonal changes on the planet, with each season lasting over 7 Earth years. The planet's axial tilt, similar to Earth's, means that its poles experience periods of prolonged sunlight or darkness, much like our polar regions. These slow, sweeping changes in Saturn's environment are visible in its rings and atmosphere, offering a fascinating contrast to the more rapid dynamics of Earth and other terrestrial planets. From a scientific perspective, Saturn is a gateway to understanding planetary systems both within and beyond our own. Its rich moon system, which includes Titan, Enceladus, and dozens of smaller satellites, is a microcosm of planetary formation processes. Observing the interactions between these moons and Saturn's rings provides valuable insights into gravitational dynamics, orbital resonance, and tidal forces. Moreover, studying Saturn's composition and behavior offers clues about the conditions that shaped the early solar system and the processes that govern giant planets throughout the galaxy. Saturn's role as a link between the inner and outer solar system is also significant. Beyond Saturn lies Uranus, Neptune, and the icy realm of the Kuiper Belt, where dwarf planets like Pluto reside. Saturn serves as a bridge between these distant worlds and the terrestrial planets closer to the Sun. Its moons, particularly Titan and Enceladus, offer a tantalizing glimpse of what icy worlds might harbor in the outer solar system, where liquid water may exist beneath frozen crusts. The planet-striking ring system also serves as a model for understanding disk-like structures found elsewhere in the universe. Saturn's rings, composed of billions of particles of ice and rock, mimic the accretion disks that form around young stars and black holes. By studying the dynamics of Saturn's rings, scientists gain a deeper understanding of the forces that shape these cosmic phenomena, from the creation of planets and protoplanetary disks to the accretion of material onto massive celestial bodies. Saturn's location and composition also make it an important subject for studying the boundaries of habitability. While the planet itself is uninhabitable, some of its moons, like Titan and Enceladus, hold promise as potential homes for life. The presence of organic molecules, liquid reservoirs, and energy sources on these moons raises questions about the conditions necessary for life to emerge and thrive. Saturn, therefore, is not just a destination for exploration, but a critical piece in the puzzle of life's potential across the cosmos. In the grand scheme of the solar system, Saturn is more than a planet. It is a natural laboratory and a cosmic sentinel. It embodies the beauty and complexity of our celestial neighborhood, offering insights into the forces that shape planets, moons, and entire solar systems. As our understanding of Saturn grows, so too does our appreciation for the intricate web of relationships that define our place in the universe. The Cassini spacecraft represents one of humanity's most ambitious and successful planetary exploration missions, a collaboration between NASA, the European Space Agency, ESA, and the Italian Space Agency, ASA. Cassini was designed to study Saturn, its rings, and its diverse moons. From its launch in 1997 to its dramatic conclusion in 2017, Cassini revolutionized our understanding of the Saturnian system, uncovering its mysteries and inspiring new questions about the cosmos. Cassini's journey began on October 15, 1997, when it was launched aboard a Titan 4B/Centaur rocket from Cape Canaveral, Florida. The spacecraft carried an advanced suite of instruments, including cameras, spectrometers, radar systems, and particle detectors, allowing it to conduct a comprehensive study of Saturn's system. To reach Saturn, Cassini performed multiple gravity assist maneuvers, including flybys of Venus, Earth, and Jupiter. These carefully planned slingshots provided the speed needed to cover the vast 1.2 billion kilometers to Saturn, a journey that took nearly 7 years. Arriving at Saturn on July 1, 2004, Cassini immediately began to exceed expectations. Its entry into orbit marked the first time a spacecraft had orbited Saturn, setting the stage for an unparalleled era of exploration. Early in its mission, Cassini captured detailed images of Saturn's rings, revealing their intricate structure and dynamic behavior. It studied the planet's atmosphere, documenting its powerful storms, high-speed winds, and mysterious hexagonal polar vortex. The spacecraft also examined Saturn's magnetic field, providing insights into its interaction with the solar wind and its influence on nearby moons and rings. One of Cassini's most notable achievements was its partnership with the Huygens probe, a lander developed by ESA. On January 14, 2005, Huygens detached from Cassini and descended to the surface of Titan, Saturn's largest moon. It became the first spacecraft to land on a body in the outer solar system, capturing images and data during its descent. Huygens revealed Titan's Earth-like landscapes, complete with river channels and lakes of liquid methane, and provided groundbreaking insights into the moon's dense atmosphere and surface composition. Over the course of its mission, Cassini made numerous discoveries that transformed our understanding of Saturn's moons. It detected geysers erupting from the south pole of Enceladus, confirming the presence of a subsurface ocean and identifying organic molecules in the plumes. These findings made Enceladus a prime candidate in the search for extraterrestrial life. On Titan, Cassini mapped vast seas of liquid methane and ethane, observed seasonal changes, and detected complex organic molecules, fueling speculation about its potential habitability. Cassini's exploration extended to Saturn's rings, where it uncovered the intricate dynamics shaping these ethereal structures. The spacecraft documented the effects of gravitational interactions with Saturn's moons, revealing how shepherd moons like Pan and Daphnis carve gaps and create ripples within the rings. Cassini also studied the age and composition of the rings, challenging long-standing assumptions and suggesting that they may have formed relatively recently in cosmic terms. Throughout its mission, Cassini provided a wealth of data on Saturn's magnetic field and its interaction with the solar wind. It captured stunning auroras at the planet's poles, studied plasma waves within the magnetosphere, and offered clues about the structure and rotation of Saturn's core. The spacecraft's observations helped refine models of how giant planets generate and sustain magnetic fields, contributing to broader theories about planetary interiors. Cassini's ability to perform long-term close-up observations of Saturn and its moons was unprecedented. Over 13 years in orbit, it conducted 294 flybys of Saturn's moons, returned over 635 gigabytes of data, and captured more than 4,500,000 images. Each discovery added to a rich tapestry of knowledge, deepening our understanding of the Saturnian system and its place within the solar system. The mission's success was not only scientific but also symbolic. Cassini embodied international collaboration and the pursuit of knowledge for its own sake. Its discoveries sparked public imagination and showcased the power of science and exploration. The stunning images of Saturn's rings, moons, and storms became iconic, inspiring people worldwide to look up and marvel at the universe's beauty. Cassini's journey culminated in the grand finale, a series of daring orbits that brought the spacecraft closer to Saturn than ever before. Its mission ended on September 15, 2017, with a deliberate plunge into Saturn's atmosphere, ensuring that it would not contaminate moons like Enceladus or Titan, which could potentially harbor life. This final act underscored Cassini's enduring legacy as a pioneer of planetary exploration, leaving behind a treasure trove of data that continues to fuel scientific discovery. The Cassini spacecraft's final chapter, known as the Grand Finale, was an extraordinary conclusion to one of the most ambitious missions in the history of space exploration. From April to September 2017, Cassini undertook a daring series of orbits, weaving between Saturn and its innermost rings. These unprecedented maneuvers brought the spacecraft closer to the planet than ever before, allowing it to gather groundbreaking data that would forever change our understanding of Saturn. The grand finale was carefully planned to maximize scientific returns while ensuring the protection of Saturn's moons. By the end of its mission, Cassini had uncovered compelling evidence that moons like Enceladus and Titan might harbor conditions suitable for life. To prevent any risk of contamination, NASA decided to direct the spacecraft into Saturn's atmosphere at the end of its mission, ensuring a controlled and honorable end to its journey. In the months leading up to its final descent, Cassini executed 22 daring dives between Saturn's rings and the planet itself, a region never explored before. These maneuvers allowed the spacecraft to perform close-up studies of Saturn's upper atmosphere and the inner edge of its rings. Cassini measured the density and composition of ring particles, revealing their surprisingly delicate nature. By flying so close to Saturn, it also provided detailed data on the planet's gravity, offering new insights into the mass and structure of its rings and the distribution of material within them. One of the most significant findings from the grand finale was the surprising discovery about the mass of Saturn's rings. Cassini's measurements suggested that the rings are much younger than the planet itself, potentially forming just 10 to 100 million years ago. This revelation sparked new questions about the origin of the rings, whether they resulted from the breakup of a moon, a comet, or some other celestial event. The grand finale thus opened new avenues for studying the life cycle of planetary ring systems. The spacecraft also made groundbreaking observations of Saturn's atmosphere during the grand finale. It measured the composition of the upper layers, detecting hydrogen, helium, and traces of other gases. These findings shed light on the processes shaping the planet's atmospheric dynamics, including the mysterious hexagonal storm at the North Pole and the powerful winds that sweep across its surface. By diving into this uncharted territory, Cassini provided a closer look at the forces governing one of the solar system's most iconic planets. As the end of the mission approached, the grand finale became an emotional moment for the scientists and engineers who had worked on Cassini for decades. On September 15, 2017, the spacecraft made its final plunge into Saturn's atmosphere, transmitting data back to Earth until the very last moment. In its final seconds, Cassini's instruments captured information about Saturn's temperature, pressure, and atmospheric composition, providing a fitting culmination to its historic mission. The decision to end Cassini's mission in such a dramatic way was both practical and symbolic. Practical, because it ensured that Cassini would not accidentally collide with moons like Enceladus or Titan, which could potentially harbor life. Symbolic, because it demonstrated humanity's commitment to preserving the integrity of extraterrestrial environments. Cassini's controlled descent into Saturn was a testament to the care and responsibility that guide modern space exploration. Cassini's grand finale was more than a scientific endeavor. It was a celebration of human ingenuity and curiosity. The images and data collected during this phase captured the imagination of people around the world, showcasing the beauty and complexity of Saturn up close. The mission's end was marked by tributes from scientists, space enthusiasts, and the general public, who celebrated Cassini's legacy and the many discoveries it had made possible. Even after its fiery conclusion, the grand finale continues to shape planetary science. The data Cassini collected during its final orbits remain a source of ongoing study, revealing new details about Saturn's rings, atmosphere, and magnetic field. This phase of the mission represents the pinnacle of exploration, combining risk, innovation, and discovery to expand the boundaries of human knowledge. The grand finale ensured that Cassini would forever be remembered as one of the greatest triumphs of space exploration. Its close encounters with Saturn, its rings, and its moons provided answers to long-standing questions, while posing new ones that will inspire future missions. More than just a spacecraft, Cassini was a symbol of humanity's desire to explore the unknown, pushing the limits of what is possible and deepening our connection to the cosmos. Saturn's interior structure is a realm of extreme conditions and fascinating mysteries, offering insights into the formation and evolution of gas giants. Although much of what lies beneath Saturn's clouds remains hidden, scientists have pieced together a model of its inner workings using data from missions like Cassini, as well as observations of its gravitational field, magnetic field, and atmospheric behavior. At the core of Saturn lies a dense and compact region, believed to be composed of rock and metal. This core, though small relative to the planet's immense size, is thought to weigh about 10 to 20 times the mass of Earth. Surrounding the core is a layer of metallic hydrogen, an exotic state of matter that forms under the extreme pressure and temperature found within Saturn. In this layer, hydrogen behaves more like a liquid metal, conducting electricity and contributing to the planet's powerful magnetic field. Above the metallic hydrogen layer lies a thick envelope of molecular hydrogen and helium. This region makes up the majority of Saturn's volume and gives the planet its low density, so low in fact that Saturn could float in water if a body large enough existed to contain it. The molecular hydrogen layer transitions smoothly into the visible atmosphere, where temperatures and pressures are significantly lower, creating a striking contrast between the turbulent surface and the serene, dense interior. The extreme conditions within Saturn are difficult to fathom. Temperatures at the core are estimated to reach over 200 degrees Celsius, 3,600 degrees Fahrenheit, hotter than the surface of the Sun. This heat is a remnant of Saturn's formation, as gravitational energy was converted into thermal energy when the planet accreted from the primordial solar nebula. Additionally, Saturn radiates more heat into space than it receives from the Sun, a phenomenon driven by the slow gravitational settling of helium within its interior, a process that generates additional heat as helium droplets sink through the hydrogen layers. Saturn's interior also has a profound influence on its overall structure and behavior. Its rapid rotation, completing a day in just over 10 hours, causes the planet to bulge at the equator and flatten at the poles. This oblate shape provides clues about the distribution of mass within Saturn, helping scientists refine the models of its interior. By analyzing the gravitational forces exerted by Saturn on nearby moons and spacecraft, researchers have gained a better understanding of the density variations within the planet, offering new insights into its internal composition. One of the most intriguing aspects of Saturn's interior is its interaction with the planet's magnetic field. Unlike Earth's magnetic field, which is offset from its rotational axis, Saturn's magnetic field is nearly perfectly aligned with its rotation. This alignment remains a mystery, as current models of magnetic field generation, known as dynamo theory, struggle to explain how such precision is maintained. The metallic hydrogen layer plays a key role in generating Saturn's magnetic field, but further study is needed to fully understand this complex process. Cassini contributed significantly to our understanding of Saturn's interior. By analyzing the gravitational effects of the planet on the spacecraft during its close orbits, scientists were able to detect subtle variations in Saturn's density. These measurements suggested that Saturn's core is diffuse, extending outward into the lower hydrogen layers rather than being a sharply defined region. This finding has important implications for understanding how giant planets form and evolve over time. Another puzzle lies in the nature of Saturn's deep interior and the possible presence of a helium rain phenomenon. As helium separates from hydrogen in the cooler outer layers, it forms droplets that sink toward the core. This process not only contributes to Saturn's heat emission, but also affects the composition and dynamics of its interior. Understanding this phenomenon could provide insights into similar processes occurring in most gas giants, including Jupiter and exoplanets. Saturn's interior is a study in contrasts. While its visible surface appears serene, with soft pastel hues and swirling clouds, its depths are a realm of intense heat, pressure, and dynamic activity. The interplay between these layers drives the planet's magnetic field, atmospheric patterns, and thermal emission, shaping the planet's overall behavior. As scientists continue to analyze data from the Cassini mission and develop new models, the mysteries of Saturn's interior will become clearer. Understanding the inner workings of this gas giant not only deepens our knowledge of Saturn itself, but also enhances our understanding of the processes that govern planetary formation and evolution throughout the universe. Saturn, with its hidden depths and striking beauty, remains a beacon of discovery, inviting us to explore the secrets that lie beneath its enigmatic surface. Saturn's atmosphere is a dynamic and mesmerizing world of swirling storms, high-speed winds, and subtle color variations. Despite its serene appearance from afar, the planet's upper layers are a realm of constant motion, shaped by powerful forces and complex chemical interactions. From its famous hexagonal polar vortex to its lightning-filled storms, Saturn's atmosphere reveals a planet that is both turbulent and mysterious. Saturn's atmosphere is composed primarily of hydrogen and helium, much like Jupiter and the Sun. These two elements account for over 96% of the atmosphere's mass, while the remainder consists of trace gases such as methane, ammonia, and water vapor. These minor constituents, along with complex organic molecules, contribute to Saturn's subtle golden hues and play a role in the planet's atmospheric chemistry. Unlike Earth's atmosphere, which supports life and weather patterns driven by water, Saturn's atmospheric activity is shaped by heat from its interior and the interplay of its chemical components. One of Saturn's most striking atmospheric phenomena is the hexagonal storm at its north pole, a feature that has captivated scientists since its discovery by the Voyager spacecraft in the 1980s. This bizarre six-sided structure spans over 300 kilometers, more than twice the diameter of Earth, and remains stable over decades. The hexagon's precise formation is still not fully understood, but scientists believe it is caused by a jet stream circling the pole at high speeds. Simulations suggest that the unique shape may arise from variations in wind speeds at different latitudes, creating a standing wave pattern that maintains the hexagonal structure. Saturn's atmosphere is also home to some of the fastest winds in the solar system, with speeds exceeding 1,800 kilometers per hour, 1,100 miles per hour, near the equator. These winds create powerful jet streams that define the planet's bands, which alternate between light and dark shades. These bands are less distinct than those on Jupiter, but still reveal the underlying dynamics of Saturn's weather systems. The winds are driven by a combination of solar radiation and heat escaping from Saturn's interior, creating a complex interplay that fuels the planet's meteorological activity. Another hallmark of Saturn's atmosphere is its massive storms, which can rival Earth in scale and intensity. Every few decades, a great white spot appears on Saturn, a massive storm system that encircles the planet, generating towering clouds and intense lightning. These storms are thought to arise from deep within Saturn's atmosphere, where heat and moisture build up until they erupt in dramatic outbursts. The Cassini spacecraft captured detailed images of one such storm in 2010, revealing how these tempests evolve over time. Observing these events helps scientists understand the processes that drive weather on gas giants and provides a comparison to atmospheric activity on Earth. Lightning on Saturn is another fascinating phenomenon, illuminating the dark depths of the planet's storms. These lightning bolts can be thousands of times more powerful than those on Earth, producing bursts of radio waves known as Saturn electrostatic discharges, CESs. Cassini detected these emissions, helping researchers study the frequency and intensity of lightning activity on Saturn. The presence of lightning indicates dynamic weather patterns and suggests that the lower atmosphere contains a rich mix of water vapor and ammonia. Saturn's atmosphere also changes with the seasons, which last over 7 Earth years due to the planet's long orbit around the Sun. These seasonal shifts affect cloud patterns, atmospheric temperatures, and even the appearance of the rings. For example, the hexagonal storm at the North Pole appears more vibrant during Saturn's summer, as sunlight enhances chemical reactions in the atmosphere. Cassini's long mission allowed scientists to observe these changes in real time, providing a rare glimpse into the seasonal dynamics of a distant world. While the upper layers of Saturn's atmosphere are dominated by storms and winds, the deeper regions remain largely unexplored. Temperatures increase dramatically with depth, and pressures become so extreme that hydrogen transitions into a metallic state. These hidden layers are key to understanding Saturn's interior and the processes that connect the atmosphere to the planet's core. Saturn's atmospheric wonders are not only a source of scientific intrigue, but also a testament to the planet's unique beauty. The interplay of storms, winds, and chemical reactions creates a constantly changing tapestry of patterns and colors. Observations from spacecraft like Cassini have revealed an atmospheric system that is both familiar and alien, offering a glimpse into the complexity of gas giants and the forces that shape them. As scientists continue to analyze data from Cassini and prepare for future missions, Saturn's atmosphere remains a compelling subject of study. Its dynamic nature and striking features provide a window into the behavior of other gas giants, both in our solar system and beyond. Saturn's atmospheric wonders remind us of the diversity and complexity of the universe, inspiring curiosity and a deeper appreciation for the forces that govern planetary systems. Saturn's immense size and long orbital period create slow, sweeping seasons that are unlike anything experienced on Earth. With a single year on Saturn lasting approximately 29.5 Earth years, each season on the ringed giant endures for over 7 Earth years. These gradual transitions bring profound changes to the planet's atmosphere, polar regions, and iconic rings, offering a unique perspective on the effects of solar influence over time. The cause of Saturn's seasons lies in its axial tilt, which is similar to Earth's at about 26.7 degrees. This tilt means that as Saturn orbits the Sun, its northern and southern hemispheres experience alternating periods of direct sunlight and shadow, creating summer and winter. The slow progression of these seasons is a result of Saturn's vast distance from the Sun, requiring decades for the planet to complete a single journey around its parent star. One of the most visible manifestations of Saturn's changing seasons is the variation in its atmospheric patterns. During the summer months in either hemisphere, the increased sunlight triggers chemical reactions in the atmosphere, producing hazes that give the planet a golden glow. Conversely, in winter, the reduction in sunlight causes the hazes to dissipate, revealing deeper and darker cloud layers. These seasonal shifts are particularly noticeable at the poles, where dramatic changes occur in temperature and cloud structure. The hexagonal storm at Saturn's North Pole, one of its most famous atmospheric features, undergoes significant changes with the seasons. During the winter, the hexagon is shrouded in darkness, but as the northern hemisphere transitions into spring and summer, sunlight illuminates the structure, enhancing the visibility of its striking six-sided pattern. The The seasonal increase in ultraviolet light also drives photochemical reactions that create a bluish hue around the polar region, a phenomenon observed by the Cassini spacecraft. Saturn's rings, though composed of ice and rock, are not immune to seasonal effects. The angle at which sunlight strikes the rings changes as the planet orbits the sun, creating dramatic shifts in their appearance from Earth's perspective. During Saturn's equinoxes, when the sun is directly above the equator, the rings appear almost edge-on and seem to vanish. In contrast, during solstices, the rings are fully illumined, showcasing the way all life resides on the planet and the Earth. These changing perspectives have allowed astronomers to study the rings in greater detail, revealing features such as vertical structures and seasonal variations in particle composition. Titan, Saturn's largest moon, also experiences the effects of the planet's long seasons. Its thick atmosphere and methane-based weather system respond to the changing sunlight, with seasonal shifts driving the formation of clouds, rain, and surface changes. During Titan's summer, methane clouds gather in the atmosphere, leading to intense rainstorms that shape its rivers and lakes. Observing these patterns on Titan provides valuable insights into how seasonal cycles influence other worlds with complex atmospheres. The long duration of Saturn's seasons means that observing their full cycle requires decades of continuous monitoring. The Cassini spacecraft provided an unprecedented opportunity to study these changes over time, as its mission spanned nearly half of a Saturnian year. Cassini's observations captured seasonal transitions in real time, offering a unique window into the interplay of solar energy and Saturn's dynamic system. Saturn's seasons also highlight the delicate balance of forces that govern its behavior. The energy from the sun, though much weaker at Saturn's distance compared to Earth, still plays a crucial role in shaping the planet's atmosphere and driving changes in its rings and moons. These interactions underscore the interconnectedness of the Saturnian system, where even the faintest influences have far-reaching effects. As researchers continue to analyze the wealth of data from the Cassini mission, the study of Saturn's seasons remains a priority. Understanding how the planet responds to the slow dance of sunlight and shadow offers not only a deeper appreciation of Saturn's unique characteristics, but also broader insights into how seasoned star systems have developed and how they have swung to favor planets, including those in distant star systems. Saturn's seasonal changes remind us of the scale and majesty of its system. The planet's slow, deliberate transitions are a testament to the complexity of the universe and its ability to create worlds that are both alien and profoundly familiar. These cycles, measured in decades rather than days, offer a cosmic perspective on time, inviting us to explore and marvel at the intricate rhythms of our solar system. Saturn's magnetic field is a powerful and mysterious force, enveloping the planet in a protective bubble known as the magnetosphere. This invisible structure shields Saturn and its moons from the solar wind, a stream of charged particles emanating from the sun, and plays a vital role in shaping the planet's environment. Despite being the second largest magnetic field in the solar system after Jupiter's, Saturn's field exhibits unique characteristics that continue to intrigue scientists. Generated deep within Saturn, the magnetic field arises from a dynamo effect in the planet's interior. This process occurs as metallic hydrogen, an exotic state of hydrogen formed under immense pressure, circulates within the planet's core. The movement of this electrically conductive material generates a magnetic field that extends far into space. Saturn's magnetic field is nearly symmetrical and almost perfectly aligned with its axis of rotation, a feature that sets it apart from Earth's or Jupiter's tilted magnetic fields. One of the most striking features of Saturn's magnetosphere is its immense size. It stretches hundreds of thousands of kilometers into space, creating a region where the planet's magnetic influence dominates over the solar wind. If visible, the magnetosphere would appear many times larger than Saturn itself, dwarfing its rings and moons. Within this vast structure, charged particles are trapped, forming radiation belts similar to Earth's Van Allen belts, but far more extensive. Saturn's magnetic field interacts dynamically with its moons and rings, creating a complex and interconnected system. The field's influence is most evident in the interactions with Enceladus, one of Saturn's most intriguing moons. Enceladus ejects water vapor and ice particles into space through geysers at its south pole, and these particles become ionized and incorporated into Saturn's magnetosphere. This interaction contributes to the creation of the E-ring and alters the flow of charged particles within the magnetic field. Auroras at Saturn's poles are another captivating manifestation of its magnetic field. These glowing displays of light occur when charged particles from the solar wind collide with molecules in Saturn's upper atmosphere, causing them to emit light. Unlike Earth's auroras, which are strongly influenced by the planet's tilted magnetic field, Saturn's auroras are more symmetric due to the alignment of its magnetic and rotational axes. Cassini captured stunning images of these auroras, providing insights into the interactions between the solar wind and Saturn's magnetosphere. Saturn's magnetosphere is not a static structure. It is constantly shaped and reshaped by the solar wind and the movement of particles within the field. The boundary between the magnetosphere and the solar wind, known as the magnetosphere, fluctuates in response to changes in solar activity. These interactions create waves and oscillations within the magnetic field, which Cassini's instruments were able to detect and analyze. Understanding these dynamics helps scientists study how magnetic fields behave on other planets and even stars. Despite the extensive data collected by Cassini, many questions about Saturn's magnetic field remain unanswered. For example, the near-perfect alignment of the magnetic field with Saturn's rotation challenges existing models of dynamo theory, which typically predict some degree of misalignment. Additionally, the precise structure and behavior of the planet's core, which drives the magnetic field, are still subject of ongoing research. The study of Saturn's magnetic field also provides a comparative perspective for understanding Earth's magnetosphere and its role in protecting our planet from harmful solar radiation. By observing the similarities and differences between these magnetic fields, scientists can refine their models of planetary magnetism and gain insights into the conditions necessary for habitability. Saturn's magnetic field is more than just a protective shield. It is a dynamic and integral part of the planet's identity. Its interactions with the rings, moons, and solar wind create a constantly evolving environment that highlights the complexity of the Saturnian system. As scientists continue to analyze the data from Cassini and explore the mysteries of magnetic fields throughout the universe, Saturn's magnetosphere remains a beacon of discovery, revealing the invisible forces that shape our solar system. Saturn's rings are among the most iconic and mesmerizing features in the solar system. Stretching over 2,800,000 kilometers from the planet's surface, they are composed primarily of water ice, with traces of rock and dust. Their intricate structure, shimmering beauty, and dynamic behavior have captivated astronomers and laypeople alike for centuries. Understanding the origins and evolution of these rings has become a cornerstone of Saturnian science, revealing not only the history of the planet, but also the processes that govern planetary ring systems. The precise age of Saturn's rings remains one of the most debated topics in planetary science. Early theories suggested that the rings formed alongside Saturn itself over 4 billion years ago, as remnants of the primordial solar nebula. However, more recent observations, particularly from the Cassini mission, have challenged this idea. Measurements of the rings' mass and their relatively pristine appearance suggest they may be much younger, perhaps as recent as 10 to 100 million years old. This surprising revelation raises the possibility that the rings are a transient feature in Saturn's long history. One prominent hypothesis for the formation of the rings involves the destruction of a former moon or comet. This celestial body, potentially a large icy moon, may have ventured too close to Saturn and crossed its Roche limit, the critical distance within which tidal forces can tear apart a celestial object. As the moon disintegrated, its fragments spread out to form the rings we see today. The theory is supported by the composition of the rings, which closely resembles that of icy moons in the Saturnian system, and by their relatively young appearance. The Cassini spacecraft contributed significantly to understanding the rings' origins and dynamics. By analyzing the gravitational influence of the rings during its close orbits, Cassini determined that the rings have a surprisingly low mass, comparable to that of a small moon. This finding supports the idea that the rings could not have persisted for billions of years without being eroded by micrometeoroid impacts or spreading out due to internal collisions. These measurements, combined with the observed cleanliness of the icy particles, suggest that the rings are a more recent addition to Saturn's system. The rings themselves are divided into several distinct regions, each with unique characteristics. The main rings, labeled A, B, and C, are dense and bright, while the outer E ring is faint and diffuse, composed of particles ejected from the moon Enceladus. Within the rings are numerous gaps, such as the Cassini division, created by the gravitational influence of Saturn's moons. These gaps and the structures within the rings, such as waves and ripples, are a testament to the dynamic forces at play in this intricate system. Gravitational interactions between the rings and Saturn's moons play a key role in maintaining their structure. Moons like Pan and Daphnis, known as shepherd moons, orbit within the rings and use their gravitational pull to carve gaps and create wave patterns. These interactions ensure that the rings remain organized and prevent the particles from dispersing into space. The relationship between the rings and the moons provides a natural laboratory for studying orbital mechanics and the effects of gravitational resonance. Despite their ethereal appearance, Saturn's rings are not static. They are constantly evolving due to collisions between particles, interactions with the planet's magnetic field, and the gradual influence of micrometeoroid impacts. Over time, these processes cause the rings to lose material, either through ejection into space or by falling onto Saturn's surface. This ongoing erosion suggests that the rings may eventually disappear, leaving behind only faint traces of their former glory. The study of Saturn's rings also has broader implications for planetary science. Rings like Saturn's are thought to form around young planets and stars during their early stages of development. By observing the behavior of Saturn's rings, scientists gain insights into the processes that shaped the formation of the solar system and other planetary systems across the galaxy. The rings serve as a scaled-down model of larger cosmic phenomena, such as the accretion disks that form planets and stars. The question of why Saturn has such prominent rings, while other gas giants like Jupiter, Uranus, and Neptune do not, remains a subject of interest. While these planets also have ring systems, they are far less substantial and less visible than Saturn's. This difference may be due to variations in moon systems, the timing of celestial events, or the specific conditions under which the rings form. Comparing Saturn's rings to those of other planets helps refine theories about ring formation and the unique circumstances that allowed Saturn's rings to flourish. Saturn's rings are a reminder of the ever-changing nature of the cosmos. They are both a product of destruction, born from the disintegration of a moon or comet, and a testament to the delicate balance of forces that shape planetary systems. Their shimmering beauty and the intricate structure continue to inspire wonder, while their origins and evolution challenge scientists to delve deeper into the mysteries of the universe. As we uncover more about Saturn's rings, we are reminded of the interconnectedness of all celestial phenomena, from the smallest particles of ice to the grand dynamics of the solar system. Saturn's rings are a masterpiece of celestial engineering, a sprawling structure composed of countless particles, ranging in size from tiny grains of ice to massive chunks the size of mountains. Their beauty, complexity, and intricate behavior make them one of the most fascinating phenomena in the solar system. Despite decades of observation, Saturn's rings continue to pose mysteries about their formation, composition, and ultimate fate. The rings are divided into 7 primary sections, labeled in the order of their discovery as D, C, B, A, F, G, and E. Each ring possesses unique characteristics, from the dense and bright A and B rings to the faint and diffuse G and E rings. The B ring, the most massive and dense of the main rings, showcases intricate structures that suggest active processes are shaping it. By contrast, the E ring, formed from particles ejected by the moon Enceladus, is far less dense and appears ghostly thin in comparison. One of the most intriguing features of the rings is their sharp boundaries and the gaps that separate them. The Cassini division, a wide, dark gap between the A and B rings, was first observed in the 17th century and remains one of the most prominent divisions. These gaps are not empty voids, but are instead sculpted by the gravitational forces of Saturn's moons. For instance, the moon Mimas creates the Cassini division through orbital resonance, pulling ring particles into specific patterns that clear out the region. Within the rings, smaller gaps and wave-like structures provide further evidence of their dynamic nature. Shepherd moons, such as Pan and Daphnis, orbit within the rings and exert gravitational forces that shape the edges and create ripples. These moons act as cosmic sculptors, maintaining the ring's structure by preventing particles from dispersing. Daphnis, for example, orbits within the narrow Keeler gap in the A-ring and creates stunning waves along the gap's edges as it passes. The particles that make up Saturn's rings are composed primarily of water ice, giving the rings their bright, reflective appearance. However, darker, non-icy material is also present, likely originating from micrometeoroid impacts or the disintegration of rocky bodies. The ratio of ice to rock varies across the rings, providing clues about their history and the processes that have shaped them over time. The purity of the ice in the main rings, particularly the A and B rings, suggests that they are relatively young, as older rings would accumulate more dark material from cosmic debris. Cassini's observations revealed that the rings are not static structures, but are constantly changing. Collisions between particles, gravitational interactions with moons, and the influence of Saturn's magnetic field all contribute to the dynamic behavior of the rings. For example, scientists observed that ring particles clump together in temporary aggregates, only to be pulled apart by tidal forces. These interactions create a constantly shifting landscape within the rings, where particles are in perpetual motion. Another mystery of the rings lies in their age and longevity. Cassini's measurements of the ring's mass and composition suggest that they may have formed relatively recently, perhaps within the last 10 to 100 million years. This challenges earlier theories that the rings formed alongside Saturn over 4 billion years ago. If the rings are indeed young, it raises questions about what event created them. Perhaps the destruction of a moon or comet that ventured too close to Saturn and was torn apart by tidal forces. The fate of the rings is also a subject of active research. Over time, particles in the rings are gradually pulled towards Saturn by gravity, a process accelerated by the planet's magnetic field. This ring rain means that the rings are slowly losing mass, suggesting they may eventually disappear, leaving only faint traces of their existence. Scientists estimate that Saturn's rings could vanish within 100 million years, a blink of an eye in cosmic time. Saturn's rings also provide a natural laboratory for studying larger cosmic phenomena. The processes observed within the rings, such as the formation of gaps and the clumping of particles, mirror those that occur in accretion disks around young stars. By studying Saturn's rings, scientists gain insights into how planets and moons form within these larger disks, and the vastness of stellar nurseries. As one of the most visually stunning features in the solar system, Saturn's rings continue to captivate scientists and the public alike. Their intricate structure, dynamic behavior, and enigmatic origin remind us of the complexity and beauty of the universe. Through continued study, these celestial masterpieces promise to reveal even more about the forces that shape planets, moons, and the very fabric of our solar system. The Roche limit is a fundamental concept in planetary science, playing a pivotal role in understanding how Saturn's iconic rings may have formed. Named after French astronomer Édouard Roche, this concept describes the minimum distance at which a celestial body, held together by its own gravity, can orbit a larger body without being torn apart by tidal forces. For Saturn, the Roche limit is a key factor in the creation and maintenance of its stunning ring system. The Roche limit occurs because tidal forces exerted by a massive planet like Saturn vary significantly across the diameter of an orbiting object. If the gravitational pull on the near side of the object is much stronger than on the far side, the difference creates a stretching force that can overwhelm the object's internal gravity, tearing it apart. This process is particularly relevant for smaller bodies, such as moons or comets that wander too close to Saturn. For Saturn, the Roche limit lies approximately 1,470,000 kilometers, about 9,1,000 miles from the planet's center. This distance coincides closely with the inner edge of the planet's rings. If a moon or icy body crosses this threshold, it can disintegrate, with its fragments spreading out to form a ring. Observations of Saturn's rings suggest that such an event may have occurred relatively recently, giving rise to the icy debris that now orbits the planet. The disintegration of a celestial body within the Roche limit is believed to be one of the primary mechanisms behind the formation of planetary rings. For Saturn, one prominent theory is that a former moon, sometimes referred to as chrysalis in speculative discussions, may have ventured too close and was torn apart by tidal forces. This event could explain not only the composition of the rings, which are predominantly water ice, but also their relatively young age, estimated at 10 to 100 million years. The Roche limit also governs the interactions between Saturn's rings and its moons. While the rings lie within the Roche limit, where tidal forces dominate, Saturn's larger moons orbit beyond this boundary, where their own gravity allows them to remain intact. This distinction helps define the structure of Saturn's system, with the rings occupying the inner region and the moons forming a more distant and stable population. Cassini provided invaluable insights into how the Roche limit shapes Saturn's rings and influences their behavior. By measuring the mass, density, and composition of the rings, the spacecraft offered evidence that their particles likely originated from a larger icy body. The proximity of the rings to the Roche limit further supports the idea that tidal disruption played a central role in their formation. The concept of the Roche limit is not unique to Saturn and has broader applications across the universe. For example, it explains why many gas giants, like Jupiter and Neptune, also have ring systems, though they are far less prominent than Saturn's. It also governs the behavior of celestial bodies in accretion disks around young stars and in the destruction of comets or asteroids passing close to planets. In extreme cases, such as a star's tidal disruption of a passing asteroid or planet, the Roche limit helps explain phenomena observed in distant star systems. Saturn's rings offer a vivid example of the Roche limit in action, where the balance of gravitational forces has created one of the solar system's most iconic features. The intricate structure of the rings, including their gaps, waves, and variations in particle size, reflects the dynamic interplay of tidal forces, collisions, and gravitational resonances. These processes ensure that the rings remain a constantly evolving system, shaped by the physics of the Roche limit. The Roche limit also raises fascinating questions about the fate of Saturn's rings. Over time, the icy particles within the rings are gradually pulled toward the planet, a process accelerated by Saturn's magnetic field and interactions with its upper atmosphere. This ring rain suggests that the rings may be a transient phenomenon, slowly dissipating over the next 100 million years. If so, they serve as a fleeting testament to the dramatic forces that shape planetary systems. By studying the Roche limit and its effects on Saturn's rings, scientists gain insights into the fundamental forces that govern celestial bodies. The destruction of a moon or icy body within this boundary illustrates the delicate balance between gravity and tidal forces, offering a glimpse into the processes that have shaped not only Saturn, but countless other systems in the cosmos. As we continue to explore the universe, the Roche limit remains a guiding principle for understanding the dynamics of planets, moons, and rings. Saturn's moons and rings form a tightly interwoven system, with gravitational forces creating a delicate dance of interactions. These relationships are key to the structure and stability of Saturn's rings, revealing how moons shape, maintain, and influence the intricate patterns we observe. From shepherd moons that sculpt gaps to resonances that create waves, the interplay between Saturn's moons and rings is a dynamic display of celestial mechanics. One of the most important roles played by Saturn's moons is that of the shepherd. Moons like Pan and Daphnis, which orbit within Saturn's A-ring, act as gravitational sculptors. As these moons move through the rings, their gravitational pull clears paths, creating gaps such as the Encke gap, carved by Pan, and the Keeler gap, maintained by Daphnis. These moons also produce stunning wave-like patterns along the edges of the gaps, with Daphnis famously creating vertical waves that rise several kilometers above the ring plane. Larger moons orbiting beyond the rings, such as Mimas, also exert a profound influence. Mimas, with its considerable gravitational pull, is responsible for the Cassini division, a wide, dark gap between the A and B rings. This gap is maintained by a phenomenon known as orbital resonance, where particles in the rings experience regular gravitational tugs from Mimas, pulling them into new orbits and clearing the region. Similar resonances with other moons create spiral density waves and bending waves throughout the rings, which are visible as ripples and ridges in detailed images. The gravitational interactions between the moons and the rings are not one-sided. The rings also affect the moons. For instance, the accumulation of ring material on the surfaces of small moons like Pan and Atlas has given them their distinctive shapes. Pan's ravioli-like form and Atlas's flying saucer appearance are the result of material from the rings being pulled onto their equatorial regions, creating ridges that are unique in the solar system. The E-ring, one of Saturn's outermost rings, is a striking example of how moons contribute to the formation and maintenance of rings. This diffuse ring is primarily composed of icy particles ejected from Enceladus's south polar geysers. As Enceladus orbits Saturn, its cryovolcanic activity replenishes the E-ring with fresh material, creating a direct link between the Moon's internal processes and the structure of Saturn's ring system. Cassini's observations of this interaction provided invaluable insights into how moons and rings can be interconnected. Beyond shaping the rings, Saturn's moons play a role in stabilizing them. Shepherd moons, by confining ring particles to specific regions, prevent the rings from dispersing over time. This gravitational corralling ensures that the rings maintain their distinct boundaries and prevents the particles from spreading outward or falling into Saturn's atmosphere too quickly. Without these moons, the rings might lose their iconic structure and dissipate much more rapidly. The dynamic interactions between moons and rings highlight the delicate balance. Their resonances with the rings shift, altering the patterns and structures within the rings. Over billions of years, these processes may transform Saturn's system entirely, redistributing material between the rings and moons, or even leading to the eventual destruction of the rings. Studying the interactions between Saturn's moons and rings offers a window into the physics of planetary systems. Similar gravitational processes occur in accretion disks around young stars, where planets form and shape the surrounding material. By observing Saturn's rings and moons, scientists gain a better understanding of how these forces operate on both small and large scales, from the microcosm of Saturn's system to the vastness of the universe. The intricate dance of Saturn's moons and rings reminds us of the interconnectedness of all celestial phenomena. These interactions, driven by gravity and time, create a system that is both beautiful and complex, constantly changing yet remarkably stable. Saturn's rings and moons are not just companions but collaborators, working together to craft one of the most extraordinary displays in our solar system. Saturn's moons are as diverse and fascinating as the planet's iconic rings. With at least 83 confirmed moons and countless smaller moonlets embedded within the rings, Saturn's satellite system is a microcosm of planetary science. These moons range from massive planet-like bodies such as Titan to tiny, irregularly shaped fragments that act as shepherds within the rings. Each moon tells a unique story, contributing to the complexity and beauty of Saturn's system. Saturn's moons vary greatly in size, composition, and behavior. The largest, Titan, is the second largest moon in the solar system, even larger than the planet Mercury. It boasts a thick atmosphere and surface features reminiscent of Earth's, including rivers, lakes, and seas of liquid methane. At the other extreme, moons like Pan and Atlas are only a few kilometers across, yet play critical roles in maintaining the structure of Saturn's rings. The moons are categorized based on their orbits and characteristics. Regular moons, such as Titan, Rhea, Dione, and Tethys, follow nearly circular orbits and are believed to have formed from the same material as Saturn. These moons are largely composed of water ice and rock, with surfaces shaped by craters, canyons, and other geological features. Irregular moons, such as Phoebe, have highly elliptical or inclined orbits and are thought to be captured objects from the Kuiper Belt or beyond. One of the most intriguing aspects of Saturn's moons is their interaction with the rings. Several smaller moons, known as shepherd moons, orbit within or just outside of the rings, using their gravity to shape and stabilize the ring structure. Moons like Pan and Daphnis carve gaps within the rings, while others, such as Prometheus and Pandora, shepherd the narrow F-ring, preventing its particles from spreading. These moons serve as natural laboratories for studying gravitational forces and orbital dynamics. Saturn's moons also exhibit a stunning variety of surface features. Mimas, often nicknamed the Death Star moon due to its massive Herschel crater, has a heavily cratered surface that speaks to its violent past. Iapetus, with its dramatic two-tone coloration, presents a stark contrast between its bright and dark hemispheres, raising questions about its unusual orbit and composition. Hyperion, an irregularly shaped moon with a sponge-like surface, tumbles chaotically through space, its low density hinting at a porous interior. Enceladus and Titan are particularly noteworthy for their potential to support life. Enceladus, an icy moon with a global subsurface ocean, ejects plumes of water vapor, organic molecules, and ice particles through geysers at its south pole. These plumes feed Saturn's E-ring and have made Enceladus a prime candidate in the search for extraterrestrial life. Titan, with its thick atmosphere and surface features shaped by methane-based weather, offers an environment that may resemble early Earth, making it a focal point for astrobiological research. Irregular moons, such as Phoebe, offer a glimpse into the outer reaches of the solar system. Phoebe's dark, cratered surface and retrograde orbit suggest it originated in the Kuiper belt before being captured by Saturn's gravity. This moon acts as a bridge between Saturn's inner moons and the icy bodies that populate the distant edges of the solar system. Saturn's moons are not isolated worlds. They are part of a dynamic and interconnected system. Their gravitational interactions with each other, the planet, and the rings create a complex web of relationships that drive the evolution of the Saturnian system. These moons act as both record keepers and architects, preserving the history of Saturn while actively shaping its present. The variety of Saturn's moons provides invaluable insights into planetary formation and evolution. By studying these satellites, scientists can explore how moons form, how they interact with their parent planets, and what conditions might support life. Saturn's moons serve as a natural laboratory, offering a glimpse into the processes that govern not only our solar system, but also exoplanetary systems throughout the galaxy. With missions like Cassini providing detailed data, and future missions like NASA's Dragonfly set to explore Titan, Saturn's moons remain a rich source of discovery. Their diversity and complexity remind us of the endless possibilities that await in the exploration of the cosmos, where every moon tells a story of creation, transformation, and wonder. Mimas, one of Saturn's most intriguing moons, is a small but captivating world with a diameter of just 366 kilometers. Despite its modest size, this icy satellite has drawn considerable attention due to its unique appearance and surprising characteristics. Mimas is best known for its resemblance to the Death Star from Star Wars, a likeness created by its enormous impact crater, Herschel, which dominates the moon's surface. The Herschel crater, which measures 130 kilometers across and nearly a third of Mimas's diameter, is the defining feature of the moon. Its central peak rises over 6 kilometers, surrounded by steep crater walls. This dramatic structure is the result of a massive collision early in Mimas's history, one that nearly shattered the moon. The impact left behind a scar so prominent that it became Mimas's most recognizable trait, inspiring comparisons to the fictional superweapon. Mimas's heavily cratered surface tells a story of a moon battered by impacts over billions of years. Unlike some of Saturn's other icy moons, Mimas shows little evidence of geological activity or resurfacing. Its lack of tectonic features or cryovolcanic activity suggests that it is a geologically dead world, with a surface that has remained largely unchanged for eons. This preservation makes Mimas an excellent record of the early history of the Saturnian system, capturing the heavy bombardment period that shaped many moons and planets. Despite its unassuming appearance, Mimas has presented scientists with a few puzzling mysteries. Measurements taken by the Cassini spacecraft revealed slight wobbles, or librations, in Mimas's orbit, hinting at possible variations in its internal structure. One hypothesis suggests that Mimas may harbor a subsurface ocean beneath its icy crust, kept liquid by tidal heating from Saturn's gravitational pull. However, the evidence for this ocean remains inclusive, and Mimas's interior continues to be a subject of ongoing research. Mimas also plays a crucial role in shaping Saturn's rings through its gravitational influence. The Moon's orbit lies just beyond the outer edge of the B ring, and its resonance with ring particles creates the Cassini division, a wide dark gap between the A and B ring. This interaction demonstrates how even a small moon can have a significant impact on the structure of Saturn's vast ring system. Mimas's gravity pulls on ring particles, clearing the region and maintaining the sharp boundaries of the rings. The relationship between Mimas and Saturn's rings highlights the dynamic interplay within the Saturnian system. The gravitational forces at work not only affect the rings, but also influence Mimas's own orbit and tidal interactions. These interactions may have contributed to the Moon's current state, including its potential internal heating and orbital librations. Despite its apparent simplicity, Mimas continues to captivate scientists and the public alike. Its Death Star-like appearance makes it one of the most recognizable moons in the solar system, while its potential for harboring a subsurface ocean adds a layer of intrigue to its story. Studying Mimas provides insights into the effects of tidal forces, the history of impacts in the Saturnian system, and the processes that shape icy moons. Mimas serves as a reminder that even the smallest celestial bodies can play critical roles in their planetary systems, from sculpting Saturn's rings to preserving the scars of ancient impacts. This unassuming moon contributes to the complexity and beauty of the Saturnian system. As future missions explore Saturn and its moons, Mimas will remain an essential piece of the puzzle, offering clues to the past and potential surprises yet to be uncovered. Iapetus, one of Saturn's most enigmatic moons, is a world of striking contrasts and mysteries. With a diameter of about 13.7 kilometers, it is Saturn's third largest moon, yet it stands apart due to its unusual two-tone coloration and a bizarre equatorial ridge that gives it a walnut-like appearance. Iapetus is a celestial oddity, inviting questions about its formation, evolution, and the forces that shaped its distinctive features. The most visually striking characteristic of Iapetus is its stark two-tone surface. One hemisphere, known as the leading side, is dark and coated with a layer of carbon-rich material, giving it a charcoal-like appearance. The trailing hemisphere, by contrast, is bright and reflective, composed primarily of water ice. This yin-yang pattern is unique among the moons of Saturn and remains one of the moon's greatest mysteries. Scientists believe the dark material on Iapetus's surface may have originated from an external source, such as particles from Phoebe, one of Saturn's outer, irregular moons. Phoebe's retrograde orbit and proximity to Iapetus suggests it could be the source of the dark material, which may have settled on Iapetus's leading hemisphere as the moon swept through Saturn's system. Once deposited, the darker material absorbed heat, causing nearby ice to sublimate and exposing more dark material in a runaway process known as thermal segregation. Adding to Iapetus's mystique is its equatorial ridge, a chain of mountains running along the moon's equator that rises up to 20 kilometers high in places, taller than Mount Everest. This ridge gives Iapetus its distinctive walnut shape and has puzzled scientists since its discovery by the Cassini spacecraft. Several theories attempt to explain its origin. including the possibility that the ridge formed as Iapetus's crust buckled during its early cooling, or that it is the remnant of a collapsed ring system that once orbited the Moon. Iapetus's orbit further sets it apart from Saturn's other moons. Unlike most of Saturn's satellites, which have nearly circular orbits close to the planet's equatorial plane, Iapetus orbits at a steep inclination of about 15 degrees and at a much greater distance, over 3.5 million kilometers from Saturn. This distant inclined orbit isolates Iapetus from the gravitational influences of Saturn's rings and inner moons, preserving its unique characteristics and contributing to its status as an outlier in the Saturnian system. The surface of Iapetus is heavily cratered, reflecting its ancient history and the lack of recent geological activity. Its icy terrain bears the scars of countless impacts, with some craters showing evidence of landslides and other erosional features. Despite its frozen and static appearance, Iapetus's surface holds clues to its early formation and the processes that have shaped it over billions of years. Iapetus also poses questions about the interior structure of icy moons. Its low density suggests it is composed primarily of water ice, with only a small fraction of rocky material. This composition, combined with its peculiar shape, may indicate that Iapetus has experienced minimal tidal heating compared to other moons, preserving its ancient, unaltered state. The moon's yin-yang coloration, equatorial ridge, and distant orbit have made it a focus of scientific curiosity and a source of inspiration for science fiction. Its appearance and unique features have been likened to a work of art, a celestial canvas painted by the forces of the cosmos. Iapetus challenges scientists to think creatively about the processes that shape moons and offers a glimpse into the diversity of environments within the Saturnian system. Studying Iapetus provides valuable insights into planetary science, including the effects of external material deposition, the dynamics of icy moon geology, and the evolution of orbits in complex planetary systems. It also highlights the importance of isolated environments, where conditions can preserve features that might otherwise be erased by gravitational or tidal forces. As future missions to Saturn are planned, Iapetus remains an intriguing target for exploration. Its mysterious ridge, contrasting hemispheres, and ancient surface hold the potential to reveal more about the moon's history and its place in the Saturnian system. Iapetus stands as a reminder of the unexpected and the unexplained, inviting us to uncover the secrets hidden within its icy shell. Hyperion, one of Saturn's most unusual moons, is a chaotic, porous world that defies conventional expectations. Irregular in shape and covered with deep, sponge-like craters, it stands out as one of the most peculiar moons in the solar system. With a diameter of approximately 360 kilometers, Hyperion is relatively small, yet its appearance and behavior have captivated scientists and challenged our understanding of moon formation and evolution. Hyperion's surface is its most distinctive feature. Covered in craters that create the appearance of a giant sponge, its surface texture is unlike any other moon in Saturn's system. These craters are unusually deep and lack the flat, smooth floors seen on many other moons. Scientists believe Hyperion's low density and porous composition contribute to this unique morphology. The moon's surface appears to absorb impacts without fully compressing, preserving its dramatic craters over long periods. The moon's composition is another factor in its bizarre appearance. Hyperion is composed primarily of water ice with a small amount of rocky material. Its low density, only about half that of water, suggests it is highly porous, with void spaces making up a significant portion of its interior. This porosity reduces Hyperion's gravitational cohesion, allowing impacts to create unusually deep craters without fully shattering the Moon. Hyperion's rotation adds to its mystique. Unlike most moons, which exhibit synchronous rotation, keeping the same face toward their parent planet, Hyperion tumbles chaotically through space. This irregular rotation is caused by its elongated shape and weak gravitational interactions with Saturn and nearby moons, particularly Titan. The result is an unpredictable orientation that makes it nearly impossible to predict which part of Hyperion's surface will face the Sun at any given time. Cassini provided invaluable insights into Hyperion during several flybys. The spacecraft captured detailed images of its sponge-like surface, revealing the crater's sharp edges and darkened interiors. Analysis of these dark areas indicated the presence of organic molecules, including hydrocarbons, which are common in Saturn's system, and may have originated from the moon Phoebe or from comets. The detection of these molecules adds Hyperion to the list of Saturnian moons with intriguing chemical compositions, offering clues to the distribution of organic material in the outer solar system. Despite its porous surface and chaotic rotation, Hyperion remains stable in its orbit around Saturn. It resides at a distance of approximately 1.5 million kilometers from the planet, far enough to avoid significant tidal forces that might disrupt its fragile structure. This distance also isolates Hyperion from the influence of Saturn's rings, allowing it to retain its unique characteristics without significant alteration over time. Hyperion's irregular shape and chaotic behavior make it a natural laboratory for studying the effects of low gravity and weak internal cohesion on celestial bodies. Its highly porous structure provides insights into how small moons and asteroids evolve in environments with minimal gravitational compression. These characteristics also make Hyperion a useful comparison for understanding similarly porous objects in the asteroid belt and beyond. The origin of Hyperion's sponge-like surface remains a topic of scientific investigation. Some researchers propose that its porosity is a remnant of its early formation, preserved due to the lack of significant tidal heating or internal activity. Others suggest that repeated impacts over billions of years gradually sculpted its surface, with the porous structure preventing complete collapse. Whatever the cause, Hyperion serves as a snapshot of the dynamic processes that shape small, icy bodies in the outer solar system. Hyperion's discovery in 1848 by British astronomers William and George Bond, alongside American astronomer William Lassell, marked a milestone in the exploration of Saturn's moons. Its unique appearance and chaotic motion have intrigued observers ever since, inspiring further study and capturing the imagination of scientists and space enthusiasts alike. As we continue to study Saturn's moons, Hyperion reminds us of the diversity and unpredictability of celestial bodies. Its porous, sponge-like appearance and chaotic rotation challenge our understanding of how moons form, evolve, and interact with their environments. Hyperion remains a testament to the complexity of the Saturnian system, a chaotic, yet stable member of the celestial family that orbits the ringed giant. Among Saturn's many moons, the shepherd moons stand out for their pivotal role in maintaining the structure and dynamics of the planet's rings. These small, irregularly shaped satellites, such as Pan and Daphnis, act as cosmic caretakers, carving gaps, shaping edges, and creating waves within Saturn's intricate ring system. Though diminutive in size compared to Saturn's larger moons, these shepherds wield significant gravitational influence, ensuring the rings remain one of the most striking features in the solar system. Pan, discovered in 1990 through images captured by the Voyager 2 spacecraft, is one of the most recognizable shepherd moons. Orbiting within the A ring, Pan is located in the Encke Gap, a 325-kilometer-wide division carved by its gravitational pull. This tiny moon measures just 35 kilometers across, yet its influence extends far beyond its modest size. Pan's gravity clears the Encke gap of ring particles, maintaining a distinct division within the rings and preventing material from filling the space. Pan's unusual appearance adds to its intrigue. Often described as ravioli or walnut-shaped, Pan features a prominent equatorial ridge that likely formed as ring material accumulated on its surface. This distinctive ridge makes Pan one of the most visually unique objects in the Saturnian system and highlights the ongoing interactions between the moon and its surrounding environment. The ridge's formation is a vivid example of how ring material can shape the moons that orbit within or near the rings. Daphnis, another Shepherd's moon, orbits within the narrow Keeler gap in the outer part of Saturn's A ring. Discovered in 2005 by the Cassini spacecraft, Daphnis is even smaller than Pan, with a diameter of only about 8 kilometers. Despite its small size, Daphnis creates dramatic effects within the Keeler gap. Its gravitational pull generates vertical waves along the gap's edges, causing particles to rise several kilometers above the ring plane. These waves, captured in stunning detail by Cassini, provide a window into the dynamic interactions between moons and ring particles. Shepherd moons like Pan and Daphnis stabilize the ring system by confining particles to specific regions. Without these moons, the rings would gradually spread out, losing their sharp boundaries and distinctive features. The gravitational influence of the Shepherd moons ensures that the particles remain in tightly confined orbits, preserving the intricate patterns and structures that make Saturn's rings so remarkable. Beyond their immediate effects on the rings, Shepherd moons also contribute to the broader dynamics of Saturn's system. Their interactions with other moons and with Saturn's gravitational field create resonances that influence the movement of particles within the rings. These resonances generate spiral density waves and bending waves, which are visible as ripples and ridges in the rings. By studying these patterns, scientists can gain insights into the forces shaping not only Saturn's rings, but also other disk-like systems, such as protoplanetary disks around young stars. The discovery and study of Shepherd moons have been instrumental in advancing our understanding of planetary ring systems. By observing how these small moons interact with the rings, scientists can develop models of ring formation and evolution that apply to other celestial systems. Shepherd moons also provide a glimpse into the processes that govern the early solar system, when planets and moons were forming from disks of gas and dust. The origins of Pan and other Shepherd moons are still a topic of investigation. Some theories suggest that these moons formed from the same material as Saturn's rings, coalescing from ring particles over millions of years. Others propose that they are remnants of larger moons that were broken apart by tidal forces or collisions. Regardless of their origins, the ongoing interaction between Shepherd moons and Saturn's rings highlights the dynamic nature of the Saturnian system. Cassini's close observations of Pan, Daphnis, and other Shepherd moons have provided unparalleled insights into their structure, behavior, and relationship with rings. The spacecraft captured detailed images of these moons, revealing surface features, shapes, and interactions that were previously unseen. These findings have enriched our understanding of the delicate balance of forces that maintains Saturn's rings and have inspired further exploration of similar systems around other planets. Shepherd moons like Pan and Daphnis may be small, but their influence on Saturn's rings is immense. They are the silent architects of one of the most beautiful and complex structures in the solar system, demonstrating how even the smallest celestial bodies can play a critical role in shaping the cosmos. Their ongoing interactions with the rings serve as a reminder of the interconnectedness of Saturn's system and the intricate dance of gravity, motion, and time that defines our universe. Among Saturn's many moons, the shepherd moons stand out for their pivotal role in maintaining the structure and dynamics of the planet's rings. These small, irregularly shaped satellites, such as Pan and Daphnis, act as cosmic caretakers, carving gaps, shaping edges, and creating waves within Saturn's intricate ring system. Though diminutive in size compared to Saturn's larger moons, these shepherds wield significant gravitational influence, ensuring the rings remain one of the most striking features in the solar system. Pan, discovered in 1990 through images captured by the Voyager 2 spacecraft, is one of the most recognizable shepherd moons. Orbiting within the A-ring, Pan is located in the Encke Gap, a 325-kilometer-wide division carved by its gravitational pull. This tiny moon measures just 35 kilometers across, yet its influence extends far beyond its modest size. Pan's gravity clears the Encke Gap of ring particles, maintaining a distinct division within the rings and preventing material from filling the space. Pan's unusual appearance adds to its intrigue. Often described as ravioli or walnut-shaped, Pan features a prominent equatorial ridge that likely formed as ring material accumulated on its surface. This distinctive ridge makes Pan one of the most visually unique objects in the Saturnian system and highlights the ongoing interactions between the moon and its surrounding environment. The ridge's formation is a vivid example of how ring material can shape the moons that orbit within or near the rings. Daphnis, another shepherd's moon, orbits within the narrow Keeler Gap in the outer part of Saturn's A-ring. Discovered in 2005 by the Cassini spacecraft, Daphnis is even smaller than Pan, with a diameter of only about 8 kilometers. Despite its small size, Daphnis creates dramatic effects within the Keeler Gap. Its gravitational pull generates vertical waves along the gap's edges, causing particles to rise several kilometers above the ring plane. These waves, captured in stunning detail by Cassini, provide a window into the dynamic interactions between moons and ring particles. Shepherd moons like Pan and Daphnis stabilize the ring system by confining particles to specific regions. Without these moons, the rings would gradually spread out, losing their sharp boundaries and distinctive features. The gravitational influence of the shepherd moons ensures that the particles remain in tightly confined orbits, preserving the intricate patterns and structures that make Saturn's rings so remarkable. Beyond their immediate effects on the rings, shepherd moons also contribute to the broader dynamics of Saturn's system. Their interactions with other moons and with Saturn's gravitational field create resonances that influence the movement of particles within the rings. These resonances generate spiral density waves and bending waves, which are visible as ripples and ridges in the rings. By studying these patterns, scientists can gain insights into the forces shaping not only Saturn's rings, but also other disk-like systems, such as protoplanetary disks around young stars. The discovery and study of shepherd moons have been instrumental in advancing our understanding of planetary ring systems. By observing how these small moons interact with the rings, scientists can develop models of ring formation and evolution that apply to other celestial systems. Shepherd moons also provide a glimpse into the processes that govern the early solar system, when planets and moons were forming from disks of gas and dust. The origins of Pan and other shepherd moons are still a topic of investigation. Some theories suggest that these moons formed from the same material as Saturn's rings, coalescing from ring particles over millions of years. Others propose that they are remnants of larger moons that were broken apart by tidal forces or collisions. Regardless of their origins, The ongoing interaction between shepherd moons and Saturn's rings highlights the dynamic nature of the Saturnian system. Cassini's close observations of Pan, Daphnis, and other shepherd moons have provided unparalleled insights into their structure, behavior, and relationship with rings. The spacecraft captured detailed images of these moons, revealing surface features, shapes, and interactions that were previously unseen. These findings have enriched our understanding of the delicate balance of forces that maintains Saturn's rings and have inspired further exploration of similar systems around other planets. Shepherd moons like Pan and Daphnis may be small, but their influence on Saturn's rings is immense. They are the silent architects of one of the most beautiful and complex structures in the solar system, demonstrating how even the smallest celestial bodies can play a critical role in shaping the cosmos. Their ongoing interactions with the rings serve as a reminder of the interconnectedness of Saturn's system and the intricate dance of gravity, motion, and time that defines our universe. Titan, Saturn's largest moon, is one of the most fascinating and Earth-like bodies in the solar system. With a diameter of 5,150 kilometers, Titan is larger than the planet Mercury and stands out as the only moon with a dense atmosphere. This thick, hazy shroud hides a surface sculpted by rivers, lakes, and seas, not of water, but of liquid methane and ethane. Titan's unique environment offers tantalizing parallels to early Earth, making it a key target for exploring the potential for life beyond our planet. Titan's atmosphere is its most distinctive feature. Composed primarily of nitrogen, with traces of methane and hydrogen, it is similar in composition to Earth's primordial atmosphere billions of years ago. Titan's atmospheric pressure at the surface is 1.5 times that of Earth, meaning a human could stand on Titan's surface without a pressure suit, though they would require protection from the frigid temperatures and a source of oxygen. The thick atmosphere creates a permanent orange haze, obscuring the surface from visible light and requiring infrared and radar instruments to penetrate it. The surface of Titan is shaped by an active methane cycle that mirrors Earth's water cycle. Methane evaporates from the moon's surface, forms clouds in the atmosphere, and rains back down, carving rivers and filling lakes and seas. These liquid methane and ethane bodies are primarily concentrated near Titan's polar regions, with some larger seas, like Kraken Mare, stretching over hundreds of kilometers. Cassini and its Huygens probe provided detailed data on these features, revealing a dynamic and evolving landscape. Titan's dunes, another striking surface feature, are formed by wind-blown hydrocarbon particles. These sand-like grains accumulate into vast dune fields, particularly near the equator, and are shaped by Titan's strong winds. The dunes highlight the moon's complex climate system, where interactions between the atmosphere and surface drive geological processes. Despite the differences in composition, Titan's dunes are reminiscent of those found in Earth's deserts. Beneath its icy surface, Titan is believed to harbor a subsurface ocean of liquid water mixed with ammonia. This hidden ocean, kept liquid by the heat generated through tidal interactions with Saturn, raises the possibility of a habitable environment. If this ocean comes into contact with organic molecules from the surface, it could create conditions suitable for life, making Titan one of the most intriguing astrobiological targets in the solar system. Titan's methane-based hydrology and thick atmosphere have led scientists to speculate about the potential for life on its surface or in its subsurface ocean. While the frigid temperatures, averaging around 99.9 dFc, 299 dFgF, would make water-based life unlikely on the surface, methane and ethene could act as solvents for chemical reactions. The discovery of complex organic molecules in Titan's atmosphere and on its surface suggests that the building blocks of life are present, even if life itself has not yet been detected. The Huygens probe, part of the Cassini mission, provided humanity's first close-up view of Titan when it landed on the Moon's surface in 2005. During its descent, Huygens captured images of river channels, floodplains, and a pebbly surface composed of water ice and hydrocarbon-rich sediments. This successful landing marked the first time a spacecraft touched down on a body in the outer solar system, providing invaluable data about Titan's composition, atmosphere, and weather. Titan's interaction with Saturn's magnetosphere also influences its environment. The Moon's atmosphere is constantly bombarded by charged particles from Saturn's magnetic field, which contributes to the production of complex organic molecules in its upper atmosphere. These molecules eventually settle onto the surface, adding to the rich inventory of chemical compounds that shape Titan's unique environment. Future exploration of Titan promises to uncover even more about this enigmatic world. NASA's Dragonfly mission, set to launch in the 2030s, will deploy a rotorcraft to fly across Titan's surface, studying its chemistry and potential habitability. Dragonfly will investigate areas of interest, such as dunes, methane lakes, and possible prebiotic features, searching for signs of prebiotic chemistry or even life. This mission represents the next step in unraveling the mysteries of Titan and its parallels to early Earth. Titan is more than just a moon. It is a world that challenges our understanding of habitability and the potential for life in the universe. Its thick atmosphere, methane lakes, and subsurface ocean offer a glimpse into the diversity of environments that exist beyond Earth. As a natural laboratory for studying prebiotic chemistry and planetary evolution, Titan stands as a beacon of scientific curiosity, inviting us to explore its secrets and imagine the possibilities it holds. The Huygens probe, a collaborative effort between the European Space Agency (ESA) and NASA, made history in 2005 as the first spacecraft to land on Titan and the first to touch down on any body in the outer solar system. Attached to the Cassini spacecraft, Huygens was designed to study Titan's thick atmosphere and mysterious surface, revealing a world that both mirrored and diverged dramatically from Earth. Its groundbreaking mission provided an unprecedented view of this alien moon and deepened our understanding of the Saturnian system. Huygens began its journey to Titan on December 25, 2004, when it separated from the Cassini spacecraft and entered a solo trajectory toward the moon. On January 14, 2005, after a 7-year journey aboard Cassini, the probe plunged into Titan's dense atmosphere at a speed of nearly 200 miles per hour, 12,400 miles per hour. Protected by a heat shield, Huygens endured intense friction and heat as it slowed down for its descent. Once safely through the upper atmosphere, Huygens deployed its parachutes, beginning a controlled descent that lasted over 2 hours. During this time, its suite of instruments collected data about Titan's atmosphere, including its composition, temperature, and pressure. Huygens revealed that Titan's atmosphere is predominantly nitrogen, with significant amounts of methane and smaller traces of other hydrocarbons. The probe also detected complex organic molecules, providing tantalizing clues about the moon's potential for prebiotic chemistry. As Huygens descended, its cameras captured the first detailed images of Titan's surface, revealing a landscape sculpted by flowing liquids. River channels snaked across the terrain, leading to dark, flat regions, interpreted as lakes or seas of liquid methane and ethane. These features resembled Earth's hydrological systems, but with methane taking the role of water, The images also showed evidence of erosion, sediment transport, and possible cryovolcanism, indicating that Titan's surface is geologically active. Huygens' landing marked a milestone in space exploration. It touched down on a surface composed of water-ice pebbles coated with hydrocarbon-rich material, in an area resembling a dried riverbed. The probe continued transmitting data for 72 minutes after landing, providing insights into the physical and chemical properties of the surface. Huygens detected a surprising lack of liquid methane at its landing site, suggesting that methane may accumulate seasonally or evaporate over time, driven by Titan's unique methane cycle. The scientific instruments aboard Huygens revealed Titan's atmosphere to be a dynamic and complex environment. The probe measured strong winds during its descent, driven by Titan's dense atmosphere and the rotation of the moon. It also detected haze layers composed of organic aerosols, which form in the upper atmosphere as sunlight interacts with methane. These aerosols gradually settle onto Titan's surface, contributing to its orange coloration and depositing organic material that could play a role in prebiotic chemistry. Huygens' success was a testament to international collaboration and technical ingenuity. The probe carried a variety of instruments, including spectrometers, gas chromatographs, cameras, and microphones. Each tool was designed to operate in Titan's extreme environment, providing a comprehensive data set that continues to inform scientific research. The images, sounds, and atmospheric data collected by Huygens offered a rare glimpse into the conditions on a moon that many believe could resemble early Earth. One of Huygens' most remarkable achievements was its role in establishing Titan as a priority for astrobiology. The discovery of organic molecules in the atmosphere and evidence of liquid reservoirs on the surface highlighted Titan's potential as a site for prebiotic chemistry. The mission demonstrated that Titan's methane cycle mirrors Earth's water cycle in many ways, raising questions about how similar processes might influence the development of life. The success of Huygens paved the way for future missions to Titan, including NASA's upcoming Dragonfly rotorcraft, which will explore the moon's surface in greater detail. Dragonfly will build on Huygens' legacy, investigating the chemistry and geology of Titan and searching for signs of prebiotic activity or even life. The data collected by Huygens provided the foundation for planetary science for decades to come. Huygens was more than a probe, it was a pioneer. Its descent and landing on Titan marked a historic moment in humanity's exploration of the solar system, demonstrating the potential for robotic explorers to reveal the secrets of distant worlds. The mission showcased the beauty and complexity of Titan, inspiring scientists and the public alike to dream of what lies beyond. Titan, Saturn's largest moon, is a world of extraordinary possibilities, offering one of the most compelling environments for exploring the potential for extraterrestrial life. With its dense atmosphere, organic-rich chemistry, and evidence of both liquid methane on the surface and liquid water beneath, Titan invites comparisons to early Earth. While the moon's frigid temperatures may seem inhospitable at first glance, the unique combination of conditions has made Titan a focal point for astrobiological research. One of the most intriguing aspects of Titan is its thick atmosphere, which is rich in nitrogen and methane. Sunlight and cosmic rays drive chemical reactions in this atmosphere, producing complex organic molecules such as hydrocarbons and nitriles. These molecules settle onto the surface, creating a layer of organic material that could serve as the building blocks for life. Titan's atmosphere resembles that of early Earth, raising the possibility that similar prebiotic chemistry could occur under the right conditions. On the surface, Titan's lakes, rivers, and seas of liquid methane and ethane form a hydrological cycle analogous to Earth's water cycle. Methane evaporates, condenses into clouds, and falls as rain, shaping the Moon's landscape through erosion and deposition. These features make Titan the only other known body in the solar system with stable liquid reservoirs on its surface. While methane and ethane are unlikely to support water-based life, they could act as solvents for chemical reactions that lead to exotic forms of life, vastly different from those on Earth. Beneath Titan's icy crust lies a hidden ocean of liquid water, likely mixed with ammonia. This subsurface ocean, kept liquid by tidal heating from Saturn's gravity, represents another potential habitat for life. Water is a key ingredient for life as we know it, and the ocean's interaction with Titan's organic-rich surface could create conditions favorable for microbial or prebiotic chemistry. The possibility of life in this hidden ocean has drawn comparisons to other ocean worlds, such as Europa and Enceladus. Titan's potential for life extends beyond its current conditions to its future evolution. As the sun ages and grows hotter over billions of years, Titan's surface temperature could rise, allowing water to become stable on its surface. In this scenario, Titan might experience a transformation similar to the early Earth, with its thick atmosphere and abundant organic material creating an environment conducive to life. This future habitability makes Titan a natural laboratory for studying planetary evolution and the conditions that foster life. The Huygens probe provided the first direct evidence of Titan's potential for life when it detected complex organic molecules during its descent through the atmosphere. These molecules, such as acetylene and hydrogen cyanide, are precursors to amino acids and other essential components of life. The presence of these compounds, combined with the discovery of methane and ethane lakes, confirmed that Titan is rich in the raw materials needed for prebiotic chemistry. Cassini further expanded our understanding of Titan's habitability by mapping its surface and studying its interaction with Saturn's magnetosphere. The spacecraft detected evidence of cryovolcanism, where water and other materials from the interior are ejected onto the surface. These processes could provide a mechanism for exchanging material between the subsurface ocean and the surface, creating opportunities for complex chemistry. While Titan's extreme cold, averaging 179 degrees CF, presents challenges for life as we know it, the Moon's unique environment has inspired theories about alternative biochemistries. Some researchers propose that life on Titan could use methane or ethane as a solvent, rather than water, and rely on hydrocarbons as an energy source. Such life forms would likely be chemically distinct from terrestrial organisms, representing a completely novel form of biology. Future missions to Titan aim to explore its potential for life in greater detail. NASA's Dragonfly mission, set to launch in the 2030s, will deploy a rotorcraft to investigate the Moon's surface and atmosphere. Dragonfly will analyze organic materials, study the chemistry of Titan's lakes and dunes, and search for signs of prebiotic activity. The mission will also probe the potential habitability of Titan's environment, building on the legacy of Huygens and Cassini. Titan's potential for life is a reminder of the diversity of environments that exist within our solar system. Its thick atmosphere, methane seas, and hidden ocean offer multiple pathways for the emergence of life, challenging us to expand our understanding of what life can be. As we continue to explore Titan, we move closer to answering fundamental questions about our place in the universe and the possibility of life beyond Earth. Enceladus, one of Saturn's most intriguing moons, has emerged as a prime candidate in the search for extraterrestrial life. Despite its small size, just 504 kilometers in diameter, Enceladus has captivated scientists with its active geology, hidden ocean, and dramatic geysers. This icy world, seemingly quiet from a distance, harbors an extraordinary environment beneath its frozen surface, offering clues to the potential for life beyond Earth. Enceladus' most striking feature is its cryovolcanic activity. At the Moon's south pole, massive geysers eject water vapor, ice particles, and organic molecules into space. These plumes, discovered by the Cassini spacecraft in 2005, originate from a series of parallel fractures known as tiger stripes. The geysers are powered by heat from tidal forces exerted by Saturn's gravity, which flexes Enceladus's interior as it orbits the planet. This process keeps parts of the Moon's subsurface warm and drives the ejection of material through its icy crust. The plumes provided the first direct evidence of the subsurface ocean on Enceladus. Analysis of the material ejected by the geysers revealed water vapor, salts, and simple organic compounds, indicating that the ocean beneath the ice is in direct contact with the Moon's rocky core. This interaction creates conditions similar to hydrothermal vents on Earth's ocean floor, where heat and minerals provide energy for life. The discovery of such an environment has made Enceladus one of the most promising places in the solar system to search for microbial life. Cassini's flybys of Enceladus offered unparalleled insights into the Moon's composition and activity. The spacecraft flew directly through the plumes multiple times, collecting samples of the ejected material. These samples included molecular hydrogen H2, a potential energy source for microbial life, as well as a variety of organic compounds. The presence of hydrogen suggests ongoing chemical reactions between water and rock, similar to processes that support life in Earth's oceans. The subsurface ocean on Enceladus is estimated to be global, extending beneath the entire icy crust. This ocean, likely tens of kilometers deep, is kept liquid by a combination of tidal heating and the insulating properties of the ice. The salinity of the ocean, inferred from the composition of the plumes, is similar to that of Earth's oceans, further strengthening the parallels between Enceladus and habitable environments on Earth. Enceladus's icy surface reflects nearly all of the sunlight that hits it, making it one of the most reflective objects in the solar system. This high albedo gives the Moon a bright, almost pristine appearance, but it also hides the dynamic processes occurring beneath. The South Pole, where the tiger stripes and plumes are located, is warmer than expected, with temperatures high enough to allow liquid water to exist just below the surface. This region is a hotspot of activity, contrasting sharply with the Moon's otherwise frozen exterior. The material ejected by Enceladus's plumes also contributes to Saturn's E-ring, a diffuse ring of icy particles that orbits the planet. Enceladus acts as a natural source of material for the ring, replenishing it with particles from its geysers. This interaction between the Moon and the ring system highlights the interconnected nature of Saturn's system, where even small moons play a significant role. Enceladus's potential habitability extends beyond its ocean and plumes. The Moon's small size and proximity to Saturn mean it experiences strong tidal forces, which could drive chemical mixing and energy transfer within its interior. These processes create a dynamic environment that may support a wide range of chemical reactions, increasing the likelihood of conditions conducive to life. Future exploration of Enceladus is a top priority for astrobiologists and planetary scientists. Proposed missions include orbiters and landers designed to analyze the plumes in greater detail or sample the icy crust directly. Such missions aim to detect more complex organic molecules, assess the habitability of the subsurface ocean, and search for direct evidence of life. Enceladus represents a unique opportunity to study an ocean world without the need for deep drilling, as its plumes provide a natural window into its interior. Enceladus is a testament to the diversity and dynamism of Saturn's moons. Beneath its frozen surface lies an active, life-supporting environment that challenges our understanding of habitability and the conditions necessary for life. As a beacon of hope in the search for extraterrestrial life, Enceladus reminds us of the potential for discovery in even the most unexpected places. The exploration of Saturn and its moons has revealed a world of wonders, but many mysteries remain unsolved. Future missions to the Saturnian system promise to build on the legacy of past explorations, such as Cassini-Huygens, and push the boundaries of what we know about this distant gas giant and its diverse satellites. These missions aim to address questions about the origins of Saturn's rings, the habitability of its moons, and the processes that have shaped the planet's dynamic system. One of the most anticipated upcoming missions is NASA's Dragonfly, set to launch in the mid-2030s. Dragonfly is a rotorcraft designed to explore Titan, Saturn's largest and most Earth-like moon. Equipped with advanced scientific instruments, Dragonfly will fly across Titan's diverse landscapes, studying its dunes, lakes, and potential cryovolcanic regions. The mission's primary goals include analyzing Titan's organic-rich surface for signs of prebiotic chemistry and assessing its potential to support life. Dragonfly's mobility will allow it to visit multiple sites, providing a comprehensive view of Titan's geology, chemistry, and climate. In addition to Titan, Enceladus remains a top priority for exploration. The discovery of water plumes containing organic molecules makes Enceladus one of the most promising candidates for hosting life in the solar system. Proposed missions to Enceladus include orbiters and landers that could sample its plumes directly, searching for complex recoils lifetime after time. Concepts such as the Enceladus Life Finder and the Orbilander propose to analyze the moon's geysers and icy surface, providing a deeper understanding of its subsurface ocean and its potential for habitability. Saturn's rings and their origins also remain an area of scientific curiosity. Future missions could focus on determining the precise age and composition of the rings, addressing questions raised by the Cassini spacecraft's findings. Proposed spacecraft could carry instruments capable of studying the fine structure of the rings and the role of micrometeoroid impacts in shaping their evolution. Understanding Saturn's rings could offer broader insights into the formation of disk systems across the universe, from planetary rings to protoplanetary disks around young stars. Other potential missions might target Saturn's smaller moons, such as Iapetus, Hyperion, or the shepherd moons within the rings. These moons hold clues about the formation and evolution of Saturn's system. For example, Iapetus's two-toned coloration and equatorial ridge are features that could be investigated in greater detail with high-resolution imaging and surface sampling. The Hyperion's porous, sponge-like surface and chaotic rotation present another unique target for understanding the dynamics of irregular moons. Advancements in technology are driving new mission concepts that could transform our understanding of the Saturnian system. For instance, small, low-cost spacecraft and CubeSats are being considered for reconnaissance missions to Saturn's moons and rings. These smaller platforms could complement larger missions, conducting focused studies or serving as scouts to identify key areas for future exploration. International collaboration is expected to play a significant role in future missions to Saturn. The success of the Cassini-Huygens mission demonstrated the power of partnership between agencies like NASA, ESA, and ASI. Future efforts could build on this model, combining resources and expertise to tackle the logistical and financial challenges of exploring the outer solar system. The challenges of returning to Saturn are considerable. The vast distance from Earth means missions require years of travel time and significant fuel resources. Advances in propulsion technologies, such as solar electric propulsion or nuclear thermal propulsion, could help overcome these hurdles, enabling faster and more efficient travel to the Saturnian system. Long-duration missions also require innovations in spacecraft autonomy, as communication delays make real-time control from Earth impractical. While no missions are currently planned to revisit Saturn itself, future exploration concepts include probes designed to study its atmosphere and magnetic field in greater detail. These probes could descend into Saturn's thick clouds, analyzing their composition and dynamics, or deploy instruments to study the planet's powerful magnetic environment. Such missions would complement studies of Saturn's moons and rings, offering a holistic view of the system. As the exploration of Saturn continues, the discoveries made there could reshape our understanding of the solar system and our place within it. Saturn's moons, rings, and atmosphere are not only objects of scientific curiosity, but also windows into the processes that govern planetary systems across the galaxy. Future missions hold the promise of uncovering new wonders and answering some of humanity's most profound questions about the nature of life and the universe. The Cassini mission stands as one of the most ambitious and successful endeavors in the history of planetary exploration. Over its 13 years in orbit around Saturn, Cassini revolutionized our understanding of the planet, its rings, and its moons. Its groundbreaking discoveries not only answered long-standing questions, but also raised new ones, ensuring that Saturn will remain a focus of scientific inquiry for decades to come. Cassini's journey began with its launch in 1997 as a collaboration between NASA, the European Space Agency, ESA, and the Italian Space Agency, ASA. After a 7-year voyage, it arrived at Saturn in 2004, becoming the first spacecraft to orbit the gas giant. Equipped with a sophisticated suite of instruments, Cassini conducted detailed studies of Saturn's atmosphere, magnetic field, and ring system, providing data that transformed our understanding of this distant world. One of Cassini's most significant contributions was its exploration of Saturn's moons. The spacecraft's close encounters with Titan revealed a world shaped by liquid methane, with rivers, lakes, and seas sculpting its surface. Cassini's radar mapped Titan's hidden landscapes, while its spectrometers identified complex organic molecules in the moon's thick atmosphere. These findings confirmed Titan as a key target for future astrobiological studies, offering insights into prebiotic chemistry and the potential for life. Enceladus was another highlight of Cassini's mission. The discovery of water plumes erupting from the moon's south pole was a defining moment, revealing the existence of a global subsurface ocean. Cassini's analysis of these plumes identified water vapor, salts, and organic molecules, providing evidence that Enceladus could host habitable conditions. These findings established Enceladus as a prime candidate in the search for extraterrestrial life, reshaping the priorities of future exploration. Cassini also provided unparalleled insights into Saturn's iconic rings. The spacecraft studied the structure, composition, and dynamics of the rings, revealing their intricate relationship with the planet and its moons. Cassini's observations suggested that the rings may be much younger than Saturn itself, possibly formed within the last 100 million years. The discovery of wave patterns, gaps, and vertical structures within the rings highlighted the ongoing interactions between ring particles and shepherd moons, showcasing the dynamic nature of this celestial system. In its final phase, the grand finale, Cassini undertook a series of daring dives between Saturn and its innermost rings, venturing closer to the planet than ever before. These orbits allowed the spacecraft to measure Saturn's gravity and magnetic fields with unprecedented precision, revealing details about the planet's interior structure and the age of its rings. Cassini's final plunge into Saturn's atmosphere in 2017 marked the end of its mission, ensuring that the spacecraft would not contaminate potentially habitable moons like Titan and Enceladus. Cassini's data archive continues to be a treasure trove for scientists, with over 635 gigabytes of data collected, including more than 4.50000 images. The mission's findings are still being analyzed, yielding new discoveries years after the spacecraft's end. Cassini's legacy extends beyond its scientific achievements. It has inspired a new generation of researchers, engineers, and explorers, demonstrating the power of international collaboration and the value of long-term investment in space exploration. The mission's success lies not only in its discoveries, but also in the way it redefined our relationship with the cosmos. Cassini revealed Saturn as a dynamic and interconnected system, where rings, moons, and the planet itself interact in ways that challenge and enrich our understanding of planetary science. The stunning images captured by Cassini of Saturn's rings, its swirling storms, and its distant moons have become iconic symbols of humanity's quest to explore the unknown. Cassini's legacy also extends to the future. The mission laid the groundwork for upcoming explorations, such as NASA's Dragonfly mission to Titan and proposed missions to Enceladus and Saturn's rings. These efforts will build on Cassini's discoveries, pushing the boundaries of what we know about the Saturnian system and the possibilities for life in the outer solar system. Ultimately, Cassini's legacy is a testament to the power of curiosity and exploration. It reminds us that even in the farthest reaches of our solar system, there are worlds of wonder waiting to be discovered. Cassini unlocked the mysteries of Saturn and its moons, but it also left us with new questions, ensuring that the journey of discovery continues.